Now, the intersection of two sets describes the members or items that are in both sets. Now, you might notice that there's an intersection because you've put your data into a Venn diagram and you can clearly see that there's a crossover or an overlap. Or it might be that you're looking at two lists of sets and you can see that there are some items that are in both lists. Either way, we can describe the intersection of sets A and B by writing the letters A and B, if that's the name of our sets, and then putting this sort of upside down U here. It's sort of like a little bit like a hump. Now, I've written there that it looks like an N. I'm not sure why, but when I first learnt this, I think I recalled that this is an intersection, and I said it like that to remind me that it looks like an N. When we learn about unions, you'll see that they're actually drawn like a U, and U is the first letter of the word union. So that one's easy to remember. U is a union, and the converse of it, the flip up of it, is an intersection. That might help you remember which one is which. Now, if there isn't an intersection, or if the intersection contains no items at all, then we can say that the intersection between A and B is actually just an empty set, and we can use this notation that we've just learnt to write that really quickly and easily. Now, I've got two examples here. They're quite different. They're different because they're different types of Venn diagrams. In this one, I've surveyed my class and I've asked people, have you been to New Zealand? Have you been to the United States of America? Or have you not been to either? Or have you been to both? So 3 students have been to both, 4 have been to New Zealand, 1 has only been to the USA, but not New Zealand, and 7 haven't been to either of those countries. So here I haven't listed the individual students' names. I could have done, it wouldn't take too long, there's not too many of them, but instead I've just written how many there were. In this Venn diagram, I've done something different. I've looked at the numbers on a die, and I know that there's the numbers 1 to 6, and I've got a set called odd numbers, and I've got another set called even numbers. And there's 3 in each set, but rather than writing a 3 here and a 3 here, which might be confusing, because we might think that that's just like the number on the die being 3, I've written what the actual numbers are, 1, 3 and 5, and 2, 4 and 6. Now, you'll notice that in this one, there actually isn't an intersection because a number can't be odd and even in this group. So, we have no intersection. Or we could say we've got an intersection, but it's an empty set. Now, a union of 2 sets is exactly what it sounds like. If you make a union with someone, you join together with them. So a union of 2 sets contains all of the members in both sets. Now, we write the union of sets, say A and B, as A, U, B, and that's a nice way to remember it. The U stands for union. Makes a lot of sense. Now, if we put these absolute value brackets around the union of A and B, that means we want to know how many members or items are in that union. So we're not just describing the union, we're saying how many things are in it. Now, we have to be careful not to count members twice. We've got a formula here, and some people who like formulas will just memorise this and always be fine with it. But it makes sense also just to use logic, because if you remember a formula, you can also forget it. Let's have a look at what we're talking about. Now, let's pretend we've got 15 people in our class. We've done a survey to find out who does biology or chemistry, or both, or neither. And these are the number of people in each category. Now, it's pretty clear here that if I said how many people do biology and or chemistry, put your hands up, these kids are going to put their hands up, yeah, we do biology. These kids are going to put their hands up, yeah, we do both. And these 3 kids are going to go, yeah, we do chemistry. There's going to be 6 plus 2 plus 3, there'll be 11 students with their hands up. Everybody except for these 4, okay? Now, as soon as you've got your information in a Venn diagram, that question, how many people in the union of both, becomes really easy because you can see that you need all of the people that are in either biology or chemistry. And that word or comes in when we're using unions. So if you're thinking unions, think of the word or even and or. That makes even more sense, doesn't it? Okay, but somebody who hasn't drawn a Venn diagram and is just using reasoning, perhaps you might have got a question that says, in a class, there are 8 biology students and 5 chemistry students and 4 students who do neither biology or chemistry, and there's 15 students altogether. This would be a little bit of a trick question because they haven't told you how many do both, but you could work it out. you'd need to be careful, because if you just go ahead and add up the biology students, 8, and the chemistry students, 5, you're going to get too many students because you've counted these people twice. So it makes sense then that you need to take them off, because if you've already counted them in the biology bubble, there's no point counting them again when you add on the people who do chemistry as well. So this formula now should make some sense. You take all the people in set A, add them to the things in set B, and take off anything that's in the intersection. But as I said, this formula works, it makes sense, but it also is very logical just to draw up a Venn diagram and just have a look at it and go, oh, I need these people, and these people, add them up. To me, that's more logical and an easier way to do it. Now a subset, again, is exactly as it sounds. It's a set that's inside another set. So if we've got two sets, let's say A and B, then we would say that A is a subset of B if, and only if, every single item that's in set A is also in set B. And this happens quite often when we do surveys or we're looking at data. Now we write this as A and B, and we put this, what looks like a C shape between them. Now instead of thinking of it as a C shape, I actually think of it as almost like an arrow. It's sort of pointing at the B in my mind. Again, this is just my brain making sense of it. Because to me, the C kind of doesn't make any sense, and it's not helpful for me to remember. But I sort of think of it as this is sort of pointing at the B in my mind. And that reminds me that everything that's in this is also a part of that. Now, some examples. All the girls in this room are people. So if we've got a set and we call it the people in this room, then all the girls in this room are also part of that bigger set. But there'd be some people in the room, if there's some boys in the room, who are not part of the girls in the room, but they are part of the bigger set of people in the room. And so if we drew this as a Venn diagram, and here I've just described the people, I don't need to actually list them, I can just describe people in the room, and that's this big circle. And then inside that, I've got a subset, girls that are in the room. Now, who would be outside both circles? Obviously, everybody in the world that is not in this room. So that's a lot of people, too many for me to list. And in fact, I haven't even bothered listing them, but I could write people outside this room, because that's the opposite of people who are inside the room. Similarly, down here, I've got a subset of a bigger set. Here, I've actually listed each of the items, and they happen to be numbers. They could be words, letters, people's names, anything we like. But 1, 2, and 3 are clearly also in this larger set that contains 1, 2, 3, 4, and 5. So we can see that this smaller set here is actually a subset of the set that's got more in it, or the bigger set. And if I drew this as a Venn diagram, not writing how many are in each group, but actually listing the items, we know that we can do it both ways, then 1, 2, and 3 are actually a subset inside the bigger group. The bigger group contains all those 5 numbers, 1, 2, 3, 4, and 5. But 4 and 5 are not in this smaller group, this subset that's inside. And I can write it this way, and I think of it as these guys are a part of a bigger group. And the last of our little definitions, the universal set. The universal set is a group containing everything that's in a particular set and not in it. So if we have some set called A, and we could define it however we like, then it's the union of A and not A, which we can write like this, a union of A and not A, and we call this universal set E. Now this makes heaps of sense because E stands for everything. It contains everything in the universe, no matter what you've defined your set as. So A, your set could be people who like ice cream. Well, if you join those with the people who don't like ice cream, you've got everybody, I suppose, except against people who couldn't decide if they liked it or not. But take any black and white situation, and if you include both, you've got everything. Now, while we're on this, what would happen if you tried to look at an intersection of A and not A? Well, if you've got a black and white situation where everybody's either in or out, they are A or they're not A, then there is no intersection, is there? Those are two sets that don't have any crossover. And so what you're going to get is an empty set because there is no intersection.